Hello all. Our next chapter is distributed deadlock detection algorithm, and this chapter you can refer from Distributed Operating Systems by P.K. Sinha book. Now, deadlock is a condition wherein the set of processes in a distributed system is not able to proceed further or is not able to complete its execution because of the reason that they need some resource which is being held by another process, and the same is true for all other processes. So that is a condition. Like, for example, let us say if we have two processes P1 and P2. Let us say P1 is requesting for a resource R1 to complete its execution, but that resource R1 is being held by process P2. Similarly, P2 also need a resource, say R2, which is being held by process P1. Now, this is a deadlock condition because P1 needs R1 to finish its execution. Similarly, P2 needs R2 to complete its execution, and both R1 and R2, they are not free. They are also being held by another process who is also waiting for some resource to be available. Now, this is a circular wait condition wherein the process P1 and P2, they are waiting in a cycle. Now, in this scenario, neither P1 nor P2 will be able to finish its execution because the resource that they need is not available or it's not free. So until they do not get their resource, they will not be able to complete their execution, and they will not be getting their resource because the resource is being held by a deadlocked process already. Now, in the centralized system as well as in the distributed system, this deadlock condition might occur, and hence we need to have the algorithm to deal with the deadlock condition. So similar to whatever you have studied in operating system subject, in the distributed system also we have the various mechanisms to deal with the deadlock. So those mechanism broadly has been categorized into three categories. One is deadlock avoidance, then deadlock prevention, or deadlock detection and recovery. So in this chapter, we are going to see what are the various algorithms or mechanisms that are used in distributed system to deal with the deadlock condition. Now, in a system, we will have either process or the resources. A process, as we all know, will be represented by a cycle, and the resource is represented by a rectangular box. Now, at any point in time, process can be in running state or in the blocked state. Running state means either the process is not requesting for any resource or the process has already got the resource. So, the process is executing. Blocked state means a process needs a resource which is not currently available. That means that is being held by some other process. So, in that case, the process will go into the block mode. Now, these are some of the points which you have already done in the operating system subject, but here we are going to revise a little bit. Now, in any system, whether it is a centralized system or the distributed system, there is some rule that has to be followed while using the resource. And that is, for a process to use a resource, it will have to request for that resource first. Now, the system will check if the resource is available or not. The process cannot directly start using the resource. They will have to request for it. System, after checking the status of the resource, it will be allocating the resource, and then at the end, once the process finishes the execution of the resource, it will be releasing the resource. Now, what are the necessary conditions for deadlock to occur? So, in a system, if deadlock has to happen, then there are 4 conditions that has to exist in that system. If any of these 4 conditions is not valid for that particular system, then deadlock condition in that system will never occur. So 4 conditions are mutual exclusion, hold and wait, non-preemption, and circular wait. Mutual exclusion condition means that system has resource which are mutually exclusive resource. So if a resource is mutually exclusive, it means that resource can be accessed by only one process at a time. Though n number of processes can use that resource, but it has to be executed one by one. It cannot be simultaneous. So simultaneously or at the same time, if the resource cannot be used by more than one process, then we say that the resource is mutually exclusive resource. So it says that for deadlock to occur in a system, the system should have the mutually exclusive resource. Next is hold and wait condition. Now, if a system is allowing hold and wait condition, it means that the system is allowing process to hold a resource and request for another resource. So if the system is not allowing hold and wait condition, then the process is not allowed to request for another resource if it is already holding a resource, one resource. But usually in all the systems, hold and wait condition has to be allowed, otherwise the efficiency of the system will be drastically reduced. So hold and wait condition means a process is allowed to hold a resource and wait for another resource. Next is no preemption condition. No preemption condition is a condition wherein if a process is holding a resource, the system cannot forcefully take away the resource from the process. That means the resource or the process is such that if the system takes away the resource from that process forcefully without that process voluntarily releasing the resource, then it is going to affect the integrity of the resource or integrity of the process. Then we say that the non-preemption condition is applicable in that particular system. So non-preemption means at any point in time, if a process has not voluntarily released the resource, then the system cannot forcefully take away that resource from the process. Now the last condition that has to exist for a deadlock to occur is circular wait condition. This we had discussed in the first slide. That is, a process is waiting for a resource which is being held by another process, which is again waiting for a resource being held by another process, and so on, and hence they are in a circular condition, circular wait condition. Now these are the necessary conditions for deadlock to occur. Now suppose if you have a system and you want to model whether the deadlock has occurred or not. Okay, you want to figure out the deadlock has occurred in the system or not. In that case, you need to do deadlock modeling. That means you need to represent the condition of the system, that is condition of processes and the resources of the system in some form wherein we can apply the algorithm and see whether the system is currently in the deadlock condition or not. So for that, the process and the resource, they are represented by using node. Process node is represented by circle. Resource node is represented by rectangle. Now resource can have many units. That is called instances of the resource. Suppose if it is only one unit, then having one square or the rectangle is sufficient. But if the resource has multiple units, then it is represented by dot. Now these are the nodes. Now to connect the nodes, we have edges. So there are two types of edges used in modeling deadlock. One is assignment edge and the other one is request edge. Assignment edge is if the process has already got the resource, then we use assignment edge. That is, let us say a resource is already allocated to the process. So the direction of assignment edge will be from resource to the process. Another type of edge is request edge. Request edge means process is requesting for the resource, and the direction of request is from process to the resource. So while modeling the deadlock, we are going to represent process by circle. We are going to represent resource by rectangle. We are going to represent whether the resource is allocated or process is requesting for the resource by assignment age and the request age. Now once we have done this, once we have drawn the graph, to check whether the deadlock has occurred or the system is in the deadlock condition or not, we are going to look for either cycle or not. Now if all the resources are having their only one unit, that means the number of instances of all the resources are only one, then we can simply check for the cycle. Now if the number of instances of the resource is more than one, we need to check for the not. That means, for example, in this case, in this example, this particular resource had two instances or two unit. So in that case, we need to check for not. So how we are going to, in whether it is a centralized or the distributed system, how we are going to check whether the system is in the deadlock condition or not? For that, we need to represent the system in form of graph using process node, resource node, assignment age and the request age. And in that graph, we need to check whether there is cycle or there is not present in that graph. Now two types of graph that can be drawn. One is called wait for graph, the other one is called resource allocation graph. Okay, so let us see resource allocation graph first. So in case of resource allocation graph, as I said, resource will be represented by box and process will be represented by cycle. So we will be writing the name of process and name of resources here. And there can be assignment age or there can be the request age. So this is our resource allocation graph. Now in the resource allocation graph, we will be representing resources explicitly. But it is not necessary to do so. This can be simplified by using wait for graph, wherein let us say if P1 is waiting for a resource R1 which is being held by, let us say, P2. This is our resource allocation graph, wherein which process is waiting for which resource or which resource is allocated to which process, that will be shown explicitly by using the resource node for the resource. But if we remove this resource from the graph, then also it will be understandable, and this is being done in wait for graph. So in the wait for graph, if the situation is like this, with P1 waiting for a resource that is being held by P2, we can remove the resource from this graph and we can simply directly connect P1 with the P2. So the first one is resource allocation graph, and the second one becomes the simplified version of resource allocation graph, that is wait for graph. So if there is arrow from P1 to P2, we need to understand that between P1 and P2 there is a resource. P1 is waiting for a resource which is being held by P2. So either resource allocation graph or wait for graph we can use while modeling the deadlock, and in that graph we need to check whether there is cycle or not. So for example, here this is the resource allocation graph and this is our wait for graph. So in the resource allocation graph, we can see here P1 is requesting for R2 that has been already allotted to P2. P2 is requesting for R1 which is being already allotted to P1. Similarly, R2 is also being requested by P3. Now the entire graph can be simplified by removing R1 and R2, and this will be the simplified version called wait for graph. Now there can be two types of deadlock in the distributed system. One is resource deadlock, the other one is communication deadlock. So resource deadlock means the process are not getting the resource which they need because that is being held by another process. Similarly, communication deadlock means the process needs some message or the communication which is not being released or which is not being sent by another process, because that is also waiting for a message to be received before delivering the message or before sending the message to some other process, because that it is also waiting for a message which another process is not releasing. So that is a communication deadlock. So both resource and the communication deadlock are same. In the first case, they are waiting for the resource. In the second case, the processes are waiting for the message in the circular wait manner. Now, how deadlock is handled in distributed system? Similar to centralized system, as I said, 3 techniques can be followed. One is avoidance, prevention, and the detection and recovery. So if we want to go for deadlock avoidance, then in the beginning only, the system is going to check everything and make sure that deadlock never occurs in that particular system. So that is, when a process enters the system will be collecting all the resource requirement of that process. Before allowing that process to execute, to start the execution, the system will know about all the resource requirement of all the processes that are going to enter in the system or that has entered in the system. And after knowing the resource requirement of all the process, the system will execute some algorithm, like banker algorithm in case of operating system. It is going to execute the algorithm and find out whether allowing a particular process, the system will be in the safe state or unsafe state. So safe state is a state wherein deadlock condition will not occur, and unsafe is a state wherein deadlock condition might occur. It's not the guarantee that it will occur, but it might occur. So system will check whether allowing that process to start their execution, the system is going to go into safe state or unsafe state. So if it is safe state, then process will be allowed to execute, and if it is going to be in the unsafe state, then process will not be allowed to continue further. So this is deadlock avoidance. In this case, deadlock scenario will never occur. That will be made sure by the system itself. But this avoidance technique cannot be used in the distributed system, though it is feasible, but in actual distributed system it is practically not possible, because in the distributed system, one problem is we will not know about the processes that are going to enter in the system. We will not know anything about how many processes at what time are going to enter in the system and what will be their resource requirement. And another one is the number of processes. So distributed system usually will have very large number of processes, and knowing their resource requirement and applying algorithm will not be possible in actual distributed system. Now the next, another way of handling this deadlock condition is deadlock prevention. As we had discussed previously, that there are 4 necessary conditions that has to occur in a system, that has to be present in a system, then we say that the system is in the deadlock condition. Now if we make sure that at least one of those 4 necessary conditions is not satisfied by the system, then we can say that the deadlock condition will never occur in that system. So the 4 necessary condition was mutual exclusion, hold and wait, non-preemption, and circular wait. So if we make sure that any of these 4 condition is not satisfied, then as I said, deadlock will not occur. But this condition there are such that it will be very difficult, or in some cases it will not be possible to make sure the condition is not satisfied. Let us say, for example, mutual exclusive condition. So whether a resource is mutually exclusive or not, that is the property of resource. For example, let us say printer is a resource. Printer cannot be accessed by multiple processes simultaneously. So we cannot allow that printer to be printed by more than one processes simultaneously. So it is not going to give the output that will be required. So that way, a system, whether the resources are mutually exclusive or not, that it will not be possible for us to control. Next condition is hold and wait. Now, hold and wait condition can be controlled by the system by using two mechanisms, that is called collective request and ordered request. So we can make sure that the process is not allowed to hold a resource and request for another resource. For that, one is to make the process request for all the resources in the beginning and get all the resources, and once the process has got all the resource, then only allow that process to continue further. Now in that case, hold and wait condition will never occur, because the process will already have all the resource that it needs before it had started its execution. But if we do so, this will be reducing the performance of the system, and in the distributed system the performance is one very important criteria. The next condition is non-preemption. Non-preemption means forcefully taking the resource away from the process. So non-preemption also, it is not in hand of the system. It depends on the type of process and the type of resource. Now the last condition is circular wait condition. So circular wait condition will occur if the processes are requesting the resources in form of cycle. So that if the system can control that, then deadlock prevention will be possible. So the deadlock prevention mechanism, if we apply in a system, then as we have seen that it is going to reduce the performance of the system, and which in distributed system it will not be affordable for us to do so. So usually what happens in all the distributed system is they go for deadlock detection and recovery, because the frequency of deadlock occurrence in any system is very less. That is, there will be hardly a condition wherein the system will be in the deadlock condition. But if the system goes into deadlock condition, then the entire system will not be able to function. So that is why we need to have the deadlock, the algorithm to deal with the deadlock condition. So what happens mostly in the distributed system is they go for deadlock detection and recovery mechanism. So wherein the system will allow all the process to continue as it is, but in between it keeps on checking whether the system is in the deadlock condition or not. Or if a process is not able to proceed further, then it will initiate the deadlock detection mechanisms. So wherein if the deadlock is found or detected, then some recovery mechanisms will be executed. So what is a deadlock? This has been discussed over here. In all the multiple processing system, a system wherein we have more than one processes, the deadlock condition might occur, and this will be identified by using cycle or a knot. So this deadlock avoidance we discussed. Now in the deadlock prevention, I was talking about what are the ways in which deadlock can be prevented, but it is going to affect the performance of the system. So if we want hold and wait condition to be to not to occur in the system, we can use collective request mechanism. So collective request means the process will have to request for all the resources in the beginning itself, get all the resource, then only the process will continue its execution. So in the centralized system it may be possible, but in the distributed system the performance will be drastically reduced if we go for collective request. In case of ordered request, this will deny the circular wait condition, as well as if the circular wait condition is denied by the system, then the system will not be in the deadlock condition. Now in case of ordered request, what happens is that the processes are made to request for the resource while holding another resource only if it follows the order. So wherein all the resources will also be numbered, and the process will be allowed to request for the resource in the order itself. That is, let us say if a process is holding a resource R1, then it is allowed to request resource R2, R3, R4, R5 and so on. But let us say if a process is holding a resource R5, then it is not allowed to request for the resource R3 or R2, R1 and so on. So only in one direction, if we allow the processes to request for the resource, then what will happen is ultimately the scenario will be the process will keep on releasing the resource that will become free and can be given to the other processes. So that is called ordered request. So now in this chapter, basically these are the basic thing which is also applicable in the distributed system theoretically, but practically it is not yet been it's not being done in most of the distributed system, but then we need to know about all these things. Now what algorithm is basically done in the distributed system is deadlock detection and recovery algorithm. So as I said, deadlock is allowed to occur, and if it occurs, it will be detected and recovered. Now various deadlock detection algorithm we are going to discuss in this chapter. So now we are going to see the various types of deadlock detection algorithms in distributed system. Now all the algorithm, they require this two property to be satisfied. This is very important, which says that every algorithm, every deadlock detection algorithm must satisfy progress property and safety property. So progress property says that if the system is in the deadlock condition, the algorithm will have to detect that deadlock within finite amount of time. It should not happen that the deadlock has occurred long time back and the algorithm is taking very long time to detect the deadlock. So all the deadlock detection algorithm requires progress property to be satisfied, which means that the algorithm will have to detect the deadlock within some reasonable or given amount of time. Second one is safety property. So safety property is very important, which we need to see in the deadlock detection algorithm, which says that because of delay in the message transfer, because the distributed system is on top of computer network, and there can be the condition wherein the message is delivered lately, or it has been delivered in out of order. For example, if M1 is supposed to be delivered before M2, but due to computer network it is delivering M2 before M1. So due to problem with the message delivery, it should not so happen that the system has detected the algorithm has detected that the system is in the deadlock condition, but actually the system is not in the deadlock condition. Later on we will see how this kind of scenario happens. Now this type of deadlock is called phantom deadlock. Phantom deadlock means false deadlock, which means that the system is currently actually not in the deadlock condition, but due to message transmission delay or because the message was delivered out of order, the algorithm, which after applying the algorithm in the based on the messages, it has detected that the system is in the deadlock condition, but actually it is only the communication of the message problem. The system is not actually in the deadlock condition. So the detection of false deadlock might happen by the deadlock detection algorithm, which needs to be avoided. Now, how deadlock detection will be done in the distributed system is similar to that of centralized system. Resource allocation graph or wait for graph will be drawn, and then that will be checked whether all the wait for graph of different processes will be collected, and then that will be checked whether the system is in the deadlock condition or not. Now there are three category of deadlock detection algorithm. One is called centralized, the second one is called hierarchical, the third one is called distributed. So this is an example of centralized deadlock detection algorithm. So what happens is that in case of centralized deadlock detection algorithm, one of the process will be acting as a coordinator for detecting the deadlock. All other processes, they will be drawing a wait for graph or resource allocation graph, that is called local wait for graph, and all the processes, they will be sending their graph to the central coordinator. Central coordinator will be collecting the graph from all the processes, and it will perform the union operation in all the graph. Now after combining all the uh, local wait for graph of different processes, if there is any cycle, then the central coordinator will decide about how to go for the recovery mechanisms. Like for example, here there are two site or two process S1 and S2, sorry, two system S1 and S2, and the first one is the resource allocation graph of S1. In the second part, it is the resource allocation graph of S2. Now this has been simplified in the second part, that is site S1, this is the wait for graph of S1, and this is the wait for graph of S2. Now in the centralized deadlock detection mechanism, what happens is that both the system, they will be sending their wait for graph to a central coordinator, that is S1 will also be sending as well as S2 will also be sending, and the coordinator will be combining these two graph, that is by applying the union operation. And after performing the union operation, if there is a cycle like this, then that means the system is in the deadlock condition. Now how this information will be communicated, how this wait for graph will be communicated to the central coordinator is in form of messages. Like for example, here the messages are P1 is holding a resource that is being requested by P2. Similarly, P3 is requesting for R2 that is being held by P2 in site 1. In site 2, P1 is requesting for R3 that is being held by P3. So every edge is considered as one message. So edge can be a request edge or it can be a assignment edge. So let us say if we go to site S2, R3 is being held by P3. So the message will be generated by S2 saying that R3 is allotted to P3. Now another message will also be generated by S2 saying that P1 is requesting for R3. So every edge will be translated in form of message, and that will be sent to the central coordinator. Now when these messages will be communicated to central coordinator, it depends on the type of message transmission mechanism that we are using. So it can be continuous transfer, periodic transfer, or transfer on request. If we are using continuous transfer mechanism, then every time a new edge is added, that can be assignment or the request edge, that information will be communicated to central coordinator. So if there is any change anytime, that will be immediately intimated. In case of periodic transfer, in interval, so every process, every system, they are going to send the edge information in the periodically. So after every interval. Transfer on request means when the central coordinator will be asking all the system which are going to act as a local coordinator for sending the messages, that is sending the information about their local wait for graph, then only the systems which are currently acting as a local coordinator will be sending the wait for graph information in terms of messages to the central coordinator. So three ways of message communication can be done. One is continuous transfer, periodic transfer, or transfer on request. Now this is the explanation of this figure. Let us see how the deadlock detection mechanism is working using the centralized approach. So let's say this is for the site S1 resource allocation graph. So as per this, We have resource R1, R2. Now P1 has already got the hold of R1, which P2 is requesting. P2 is holding R2, which P3 is requesting. And this is the resource allocation graph of S2, wherein there is a resource R3 which is being held by P3. So whenever we draw the resource allocation graph, we need to remember one thing, that it will be based on the resource. So if I'm a system, then I'll be drawing my resource allocation graph considering my own resources. Now process can be my local process, or it can be the process of another system. Like what I'm trying to say is that for site S1's own request is R1 and R2. Now based on that, I will check which process is requesting for R1 and which process is currently holding R1. Similarly for R2 also, I'll check which process is requesting and which process is currently holding. Now based on that, I will draw the local wait for graph. Similarly for S2, its own resource is R3. Now I'll see the processes that is either requesting or that R3 is allotted. So here we can see P3 has already got hold of R3. So I will be drawing the A's from R3 to P3, and there is no other process which is currently requesting for. So now S1 and S2, they will be sending their wait for graph to the central coordinator. So it can be it can be resource allocation graph, or it can be wait for graph, whichever is easy, you can consider it and use it. Now central coordinator has combined these two graphs and found out that there is no cycle. That is, just we need to combine it. We need to perform union operation, that similar to what you have done in graph theory, how to perform union of two graphs. Now just combine it, and this is the combined form wherein there is no cycle. That means the system is not in the deadlock condition. Now let us say after some time, here in this system 2, P3 has already got the hold of R3. Now in system 1, there is a process P1 which is currently holding R1. Now let us say after some time, P1 decided to release R1. So P1 is releasing R1 voluntarily. Okay, so first P1 is releasing R1. Now after that, let us say P1 wants to use R3. So P1 is requesting for R3. So this is the scenario that is happening after some time. So after some time, what is happening is that P1, which was holding R1 before, is releasing R1, and then it is requesting for R3. Now that means two messages will be generated. One will be S1 by S1, the other one will be by S2. So let us say S1 is generating a message M1, for example, which says that just remove the A's from P1 to R3. Okay, it is telling central coordinator that P1 is releasing R1. Now let us say S2, after that S2 is generating a message M2, which is saying that add A's from P1 to R3, because now P1 is requesting R3. So the order of message is M1 will be sent by S1, and after some time S2 will be sending M2. So central coordinator, when it will be receiving M1 in the graph which it has drawn previously, it will be removing this edge, because as per M1, P1 has released R1. So this particular edge has been removed here. And after some time, when the central coordinator receives message M2, which says that P1 is now requesting for R3, so add A's from P1 to R3. So this A's will be added from P1 to R3. Now when central coordinator receives message M1, after that M2, it will perform operation in the global wait for graph accordingly, or resource allocation graph accordingly. And then here also it finds that the system is not in the cycle. Okay, the system is not in the deadlock condition, so it is fine and correct. Okay, this is the true state. What has been represented by global wait for graph is actually the condition of the system, the entire distributed system. Now there can be a problem, and the problem is, what if the message is delivered to central coordinator out of order because of delay in communicating the messages? Okay, so the fact is M1 should be delivered to M2 first, but it may so happen that because distributed system, as I said, it is implemented on top of computer network, so computer network suffers from various types of problems, and one of them is communication delay. And because of the limitation of computer network, suppose if instead of M1 being delivered to M2 first, suppose if M2 is delivered to M1, to the central coordinator, then what will happen here is, suppose if this is your message M1 and this is sending message M2. So M2 says that to add age from P1 to R3. Now this is the current global wait for graph. Now when the central coordinator will receive M2, what it will do is it will add age from P1 to R3. So P1 to R3, previously there was no age, now the age is added. Now as and when age is added, central coordinator will find that the cycle has occurred. That means the system is in the deadlock condition, and it will initiate the deadlock recovery mechanism. And in the deadlock recovery mechanism, some process might be rolled back or some process might be terminated. So here what is happening is, because M2 was delivered before M1, central coordinator has detected deadlock, but actually that deadlock system does not occur. It is only because of the limitation of computer network. So this kind of scenario is called phantom deadlock. So this deadlock is called phantom deadlock or the false deadlock, which is nothing but a deadlock condition which actually does not exist. So we can see here that the centralized approach for deadlock detection algorithm suffers from phantom deadlock problem. Now another problem with centralized approach is it relies entirely on the central coordinator. Suppose there are n number of processes, all n processes or n number of system, then all n system will be sending their local wait for graph to the central coordinator, and the central coordinator will be overloaded. And it may so happen that the central coordinator, because of being overloaded, to deal with the deadlock condition, it may not be possible. So relying entirely on the central coordinator will have lot of problems, that if the central coordinator fails, deadlock detection cannot be done, and central coordinator, if it gets overloaded, then the first requirement, which says progress property, that is deadlock has to be detected within finite amount of time, will not be possible to achieve. So we have another approach for deadlock detection in distributed system, that is called hierarchical approach for deadlock detection. So in the hierarchical approach, instead of relying entirely on the central coordinator, the entire systems will be arranged in form of logical tree, and every parent will be acting as a controller or the representative for detecting deadlock within the subtree for its child. For example, let us say we have in this example we have site S1, S2, S3, S4. Okay. Now for S1 and S2, let us say we have a controller E. For S3 and S4, we have controller F. And for controller E and controller F, which are again sites, we have another controller G. So each site will be acting as a local controller also, because in the local wait for graph, only if they find the cycle, then they will consider that as a deadlock within itself. If it sees any cycle, then that will be resolved there itself. If not, it will be communicated further. So the hierarchical approach for deadlock detection tries to distribute the responsibility of detecting deadlock to many controllers. That is, at the lowermost level, every site will be acting as the controller for the site itself. For site S1, let us say it is controller A, which will draw the local wait for graph, and if there is cycle in the local wait for graph, that will be detected and resolved there itself. Similarly, for set of sites, we will have its parent site to take the responsibility of controller. Let us say controller E will collect the wait for graph from S1 and S2, combine, it will perform the union operation, and if there is a cycle, and that will be that is a deadlock condition which will be resolved by that parent itself. Otherwise, it will be forwarded to controller G, and which will be combining again the wait for graph which it will be getting from its child nodes, and if there is a cycle, that will be detected and resolved there itself. In the hierarchical approach also, similar to that of centralized approach, it also suffers from phantom deadlock problem. Now another thing is that even though compared to centralized approach, the detection of deadlock job has been distributed a little bit, but still it is not a fully distributed approach. So the third type of deadlock detection algorithm is fully distributed approach for deadlock detection. Now in the fully distributed approach, there are two techniques that is commonly used. There are two algorithms. One is called wait for graph based algorithm for deadlock detection. The second one is called phantom deadlock detection algorithm. So now we are going to see each one by one. So what we are going to see next is fully distributed approach for deadlock detection in distributed system. And the first algorithm that we are going to discuss in detail here is wait for graph based approach for deadlock detection. Now, irrespective of centralized approach and hierarchical approach, herein there will not be any concept of coordinator or controller. So it will be any side who might have to detect the deadlock. So any side may have to take the responsibility of detecting deadlock in the distributed system, and it will not be loaded to one side. It will not be responsibility of one side or set of side to always do the deadlock detection mechanisms. So that is what is fully distributed approach. Now the first algorithm that we are going to discuss is wait for graph based approach. In the wait for graph based approach, every site, first of all, they will be drawing a local wait for graph, and in that local wait for graph, they will be adding a node called PEX, that is external process node. Okay, it is going to contain the information about something which is unknown to that system, unknown to the site. That means site has guess about up to some extent the site has a guess about that condition, but it do not know entirely. So that is called a PEX node that will be added in the local wait for graph constructed by the site. Now how this algorithm is going to work, or on what basis this PEX will be added, is these are the two conditions. Now a site is going to add edge from PI to PEX. If PI is some process that is known to that site, is waiting for a resource that belongs to another site that is being held by some other process. So that means if a site knows that a process PI is waiting for a resource of another site which is not currently available, then for now the site do not know that the resource is being held by which another process. Okay, so it will consider this as some PEX process. So it is going to add the edge from PI to PEX. Now another type of edge that can be added to PEX is from PEX to PJ. So this edge PEX to PJ will be added if Pj is the process of another site, okay, that is not the local process, that is the process of another site, that is waiting for a resource currently being held by the process of this site. So an age from Px to Pj will be added if the process of some other site is waiting for a resource that is being held by process of the local process, you can say. That is, some other site's process is waiting for releasing the resource that is being held by its own process. In that case, Px to Pj age will be added. So let us see how it is working here. Say for example, let's say we have two sites S1 and S2, and this is the condition in S1 and this is the condition in S2. So here in S1 has the information about P1, P2, P3, and P4. S2 has the information of P1, P3, P4, how they are currently using the resource. Now how this wait for graph will be constructed is based on the resource, because in between they have, if I have to draw a resource allocation graph, then in between they have the resources which are the local resource of S1 and the resource of S2. So based on the resource, they will be drawing the local wait for graph. Now out of these processes, some process belongs to site S1 itself, some process belong to some other site. Similarly for S2 also, among P1, P3 and P5, some belong to S2 and some belong to S3. Now after constructing the wait for graph, the site will be adding process the external node that is called Px, and Px will be added based on the two rules that we have discussed previously. And the two rules are, from Px, from any process to Px, the age will be added if Pi is waiting for the resource of another site being held by any process, and Px to Pj will be added if Pj is the process of another site which is waiting for its local process to release the resource. Now based on these two criteria conditions, after adding the node Px, the age will be added. Now here in this example, an age from P1 to Px is added because we can see here P1 from the site S2, P1 is waiting for a resource that P3 is holding, waiting for a resource of another site. From the graph we can see here there is resource in between, and that resource belong to S2 for which P1 is waiting for. So that is why in site S1 knows that P1 is waiting for some resource that belongs to another site. So that is why in the local wait for graph there was no age from P1 to some other node, because age is added based on the resources. So we can see here P1 is waiting for a resource of site S2, so an age from P1 to P2 is added. Now let us say P3 is the process of S2, site S2, and P3 is waiting for the resource that is being held by the process of site S1. So from the graph of site S2 we can see here P3 is waiting for some resource that is to be released by P5. And let's say that if P5 belongs to S1, then we can say that P3 is waiting for a resource which the local process of S1 must release. Now in that case we will be adding the age from Px to P3. Now this is the updated wait for graph. So in wait for graph deadlock detection algorithm, what we do is, first of all, site will be constructing local wait for graph and a Px node will be added, and how the age will be connected, that will be governed by the two conditions that we had discussed in the previous slide. Now similarly, let us go to S2. This is the local wait for graph of S2. That is, S2 knows that P1, P5 are the process of S1. P3 is its own process, and they are using or requesting the resource in this order. Now here in S2 will also add PX node, and how the edges will be connected is, now an edge from Px to P1 is there because P1 is the process of S1 which is waiting for the resource to be released by P3, which is a local process of S2. So that is why we have an edge from Px to P1. Similarly, P3 is a local process which is waiting for the resource of another site to be released. That is this condition. We need to see the graph, okay, of the other side. From there we will be able to understand regarding how to connect the edge. So from here we can see that P3 is waiting for a resource to be released, and that resource belong to S1. So we have an edge from P3 to Px. Now this is the updated wait for graph after adding the edge Px. Now this is the first step in wait for graph based fully distributed approach for centralized deadlock detection. Now what happens is that after adding node Px, if there is any local cycle, any cycle which does not involve Px, then that is a local cycle or local deadlock condition that will be resolved there itself by the site themselves. But if there is a condition wherein there is a cycle and that has involved a node which is Px node, for example, here we have a cycle which contains some external information, some information that is not fully known to site S1, then it means that there is a possibility of deadlock in this particular distributed system. Similarly, for site S2 also it will check whether there is a cycle or not. If we see here, there is a cycle which involved the node Px, that means the system might be in the deadlock condition because some information are not known to S2. So what will be done is, either site S1 will send this updated wait for graph to S2, or S2 will send the updated wait for graph to S1. So how it will be decided that to which site the updated wait for graph has to be sent is based on the edge that is from Px to P3. So from Px to P3, if you see this, any edge from Px to Pi or Pj, to which site that particular process belongs to that site wait for graph will be sent. That means S1 will check that the outward arrow from Px to another process belongs, if it is there, then the other process belongs to which site. To that site, this updated wait for graph or only the cycle information will be sent. Now here Px is waiting for a resource for P3 to release, and P3 is a process of S2. So S1 will be sending to S2. Similarly for S2, it knows from the graph it can see here that Px is waiting for a resource of P1 and P1 is a process of S1. So S2 will be sending to S1. It's not necessary that both the sites should be sending. Later on we will see that how it will be resolved. Okay, but one of them will have to send its updated wait for graph to another site. Now how it is resolved, that we will see. It depends on the ID of site. Let us say S1 ID is 1 and for site S2 its ID is 2. So if 1 is smaller than 2, then the site will be sending its. So if my own ID is smaller than the ID of the process, okay, the ID of another site, then I'll be sending my updated wait for graph or the cycle information to that site. Otherwise I'll wait for the other site to send me the updated wait for graph. So in this case S1 will be sending to S2. Now S2, after receiving the updated wait for graph, it will be performing the union operation, that is the cycle it will be receiving and combining. After combining, this is the updated wait for graph in S2. So in S2, the updated wait for graph, after performing the union operation, we can see here that there is a cycle without Px, a cycle wherein Px node is not there. So P1, P2 and P3, P1, P2 and P3, they are in the deadlock condition. This will be identified by S2, and S2 will initiate the deadlock recovery mechanism. Now after doing the deadlock recovery, if still there is a cycle which involve Px, then S2 will decide on the another side to whom this cycle information has to be forwarded, so that the other side will initiate the recovery mechanisms. Now the next algorithm, which is fully distributed approach for deadlock detection, we are going to see is probe based deadlock detection algorithm, also called as CMH algorithm. Because this particular algorithm was jointly given by three scientists, that is Chandy, Misra and Hirsch. So this algorithm, that is probe based deadlock detection algorithm, is also called as CMH, Chandy, Misra, Hirsch algorithm. Now this probe based deadlock detection algorithm is one of the very simplest algorithm, wherein we need not be drawing any wait for graph. Okay, this algorithm work only based on the message that will be communicated from one process to another process. So herein, whenever a process figure out that the system could be in the deadlock condition, so how it is going to find out is that if a process requests for a resource, and if that process do not get that resource, so that means it will wait for finite amount of time, and if the resource is not released or given to that process, then the process will forecast that the system could be in the deadlock condition, and hence it will initiate the deadlock detection mechanism. So in the deadlock detection mechanism, what that process will do is it will create a message, and it will send that message to another process, okay, for whom it is waiting for the resource to be released. Now that process will also be forwarding to next process if it is also waiting for the resource to be released by another process. And this communicating message in the distributed system, if that message travels in a cycle, that means whichever process had initially created the message, if it gets the same message back, that means the message was communicated in a cycle, and hence the system is in the deadlock condition. So this is a very simplest approach, and very much powerful and most widely adopted approach also, wherein without drawing the wait for graph, we will be able to detect the deadlock. So what happens is that, suppose let us say this is the scenario of the entire distributed system, and let us say P1 want to use a resource which is not currently available. So it will wait for some duration, and after that also it do not get the resource that it wants, that means still the resource is not available to be used. Then it will create a message which will have three fields. First field will contain the ID of process itself, that is 1. Second field will contain the ID of sending process. So currently which process is sending this message is P1 itself. So second field will contain the ID of 1 itself. Now third field will contain the ID of process to whom the message is being sent. Now P1 is sending the message to P3. So message will be sent to that other process to whom the resource is to be released. So P1 is sending to P3. So third field will contain the ID of P3. So that is 3. So this will be created by P1, and it will be sending it to P3. Now every other node, they will be forwarding, they will be creating copy of the message, making some change in the message, and then forwarding via all the outgoing edges. That is here, P3 is also waiting for a resource to be released by P5, and it is also waiting for another resource to be released by P2. So what P3 will do is, always the first field will be left unchanged. There will not be any change that will be made. Second and third field will be changed by every intermediate processes. So second field was the ID of process which is currently sending. Now P3 is going to forward the message to P5 and P2. So second field will be changed to ID of P3, that is 3. Now third field, when it is sending to P5, it will be 5, and when the message is sent to P2, then the third field will be 2. So this is how two messages will be forwarded by P3, one to P5 and the other one to P2. Now P2 also will do the same process, and if P1 gets the same message, its own message back, so how it will identify that it is getting its own message? That is from the ID that is present in the first field. If it is its own ID, it means whatever message it had sent previously, it got it back. That means message was communicated in the cycle, which the conclusion of which is the system is in the deadlock condition. So now what will happen is, P3 will be again, P3 after sending to P2, it will again create two copy of the same message. So what it will be sending to P4 will be, first is 1, first field is 1, second field will be 2, third field is 4 because it is sending to 4. Now what it will be sending to P1 is, first field is 1, second field is P2 is sending, so it will be 2, and the third field is the ID of process which it is currently receiving, so that is 1. Now when P1 will get this message from P2, from the first field it will understand that it is its own message which it had communicated, so there is a cycle and hence the system is in the deadlock condition. So this is the very simple mechanism for detecting deadlock called probe based mechanism. So it has many advantages, one of which is we do not have to construct wait for graph, so it is simple, easy and fast. Another very important advantage is it does not suffer from the problem of phantom deadlock. So there will never be a situation wherein deadlock is detected by the algorithm but actually that deadlock condition do not occur. So this was about the various mechanisms that is being used to deal with the deadlock condition in distributed system. In detail or more examples you can go through in the book that is Distributed Operating System by P.K. Sinha. Thank you.